Oh, there we go. Okay. Any questions before we start on the actual lessons? Anything from the worksheets? Okay, let's do this lesson then. So, sort of along the same lines, but this is where it gets kind of different than gravity, because the potential energy surrounding a mass is quite small due to the gravitational constant being small and gravitational forces being small. So it only really applies to huge things, but the potential energy surrounding a single point charge is actually quite large. And so there's usefulness there, because we can actually start talking about useful energy, like in the case of a battery. So we're going to talk about three different things: electric potential, potential difference, and electric potential energy. Now, all three of those things have the word potential in them. Very poorly named, but they're all very different. So we'll go through what the difference between them is. So if a charged object is in an electric field that has an electric potential energy, blah, 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 non-uniform. Okay, so non-uniform fields. So we have uniform fields and we have non-uniform fields. You can create a uniform electric field if you have like a charged plate. So if this is a positive plate and this is a negative plate, and you set their charges to be a certain value, then like the electric field will go like this. It's kind of like the same thing as having a positive charge and a negative charge. In between, the electric field will be that. Okay, it's predictable, but anywhere up here, it's not as predictable. So a non-uniform field is one that is going, it's either different strength or different directions, and that's the case for a point charge. So just if you have a single charge, so like this positive charge here, I have the electric field going that way on that side, it goes that way on that side. And as you get further and further away, it gets smaller and smaller and smaller. So it's not uniform in any way. It actually changes quite a bit. So the potential energy surrounding a point charge, or a single charge, this is based off of, like, if I had another charge here, how much work would I have to do to bring that charge over here? Okay, so how much work would I have to do? And it's positive work because I'm going against the repulsion. Okay, and so the work I do is just F times D. And so, and you have to view this as like this work is a change in potential energy. Okay, and so the formula for electric potential energy is kind of the same as electric potential in gravity, and it is EP equals, so let's apply this FE times D. Okay, so electric force times distance. And then if we expand this FE into K Q1 Q2 over R squared times D, okay, that's our electrostatic force, then the distance and the radius are the same thing. And so you get EP equals K Q1 Q2 over R squared. Okay. Now, because EP is an energy and it's electric potential energy, so it's actually like EPE, or people write PEE. Some people call it U. Because charges can either repel or attract. So for mass, when we said mass was, the EP was negative G M1 M2 over R. This negative referred to the fact that we are relating it to R equals infinity, where G equals 0. Okay, we're going to do the same thing here, but we don't need a negative here because it can repel or attract. And so when we relate a positive charge, we're relating to when R equals infinity, EP will equal 0, and that's because the electric field is 0. Okay, so we're still relating that to a point of infinity, just like we did with gravity. Okay, so we have potential energy being K Q1 Q2 over R squared. Okay, so example, how much work must be done to bring a 4 microcoulomb charged object to within a 1 meter of a 6 microcoulomb charged object from a really long way away? So let's say we have, this is our 6 microcoulomb charge, and we have a 4 microcoulomb charge that's at R equals infinity. And so Ri is infinity. Okay, the initial radius is infinity. And then we're going to bring it here, the 4 microcoulomb charge, to within 1 meter. Okay, well, if you think about it, the EPI is going to be 0, and the EPF is going to be whatever we find it to be. And so the work done is a change in potential energy. So that's going to be EP final minus EP initial, and EP initial is 0. And so we get work equals EPF, so 9 times 10 to the 9 times 4 times 10 to the negative 6 times 6 times 10 to the negative 6, and then divide by the radius, 1. Okay, and that gives us a value of, is that going to have it here? Positive 0.216 joules. Okay, and that is our answer for that question. So notice how I'm putting positive here, because I know that positives repel each other. Okay, and so if I want to bring a positive charge closer to another positive charge, I need to input energy. Input energy. Okay. So this leads us to a next point. Energy is scalar, but can be positive or negative. Okay, positive if you have to input energy, negative if energy comes out. So how much work is done to bring a negative 7 microcoulomb charged object to within 0.5 meters of a 5 microcoulomb charged object from really far away? So we're going to do the exact same thing. EPI is still going to be 0, so we can just cut to this. EPF. Okay, the derivation is the exact same, but this time it's a negative 7 microcoulomb charge. Okay, and so all you have to really do is, so here's your negative charge, okay, and it's originally at infinity, and here's your positive 5 microcoulomb charge. All you have to do is get it in the electric field where E is not 0. So all you really need to do is give it a tiny little push, and then it'll just fly towards the positive because there's an attraction there. Okay, but it won't happen at R equals infinity because that's where E equals 0. And so if we use this equation, we get 9 times 10 to the 9 times 7, times negative 7 times 10 to the negative 6 times 5 times 10 to the negative 6, and then divide by 0.5. This comes out to be negative 0.63 joules. Okay, now this is a release of energy. Now by release, I mean that it's not like you just lose it. It releases in the form of something else, and we know that this is a delta EP, and we also know that delta EP equals negative delta EK, and so this release of potential energy will become kinetic energy. Okay, and that's because it's going to accelerate towards the positive charge. They're going to be attracted to each other. Now, if you look on your formula sheet under potential energy, okay, the last column says to use positive and negative signs. So that's what we're doing here. And so even if I had, let's say I had a negative charge going towards a negative charge, and I wanted to know how much work there was, my work would be K times negative Q times divided by R. Well, this would come out as positive. Okay, which means that I need to input energy because they repel each other. I need to actually force that negative towards the other negative. Okay, and so now we're going to be using our positives and negative signs to figure out if it's an input of energy or an output of energy. Okay. Okay, so that's electric potential energy. That's probably the easiest concept. This is probably the hardest concept, electric potential. So it's this weird concept of what happens in the space surrounding a charge. Okay, so if you were to imagine a point charge, okay, a positive charge, this charge has the potential to attract or repel other charges, okay? And so because it has the potential to do something, it has a certain energy associated with it, okay? So it actually, so if you took a point in space, like this point right here, versus, we'll call this A, versus this point right here, B, you can automatically say, okay, which point is going to have more energy associated with it, okay? And we know that if you put a positive charge right here at B versus at A, it's going to accelerate faster at B than it will at A because it has more repulsion. It's closer, and so it wants to repel it even more. Okay, so there's more energy associated with position B than there is at A. And so the whole idea of electric potential is there's potential surrounding this charge, okay? And so that's what we say, how much electric potential energy is there per unit charge, okay? So it's electric potential is V, okay? And it says voltage, but we'll get into what voltage actually is in a second. It's measured in volts, so that's fine. We can keep doing that. So it's the amount of electric potential energy, so EP, there is per unit charge, and we're going to call it big Q, okay? And so what happens is if let's say V at A is 100 joules per coulomb, okay, because it's EP per Q, joules per coulomb, then if I brought a charge to point A, and let's say that charge that I brought to A was 1 coulomb, then that charge would have 100 joules of energy associated with it. Okay, that charge would have 100 joules of energy, okay? Because it's in the field that's creating the electric potential, which is big Q, okay? Okay, what's the next part that I want to talk about? I need the formula. Okay, so the potential energy, as we saw before, is dependent on both charges, okay? And so if we kind of do a derivation here, so there's a certain potential energy associated with Q, and this is Q right here. This would be little q, okay? The Q that I'm bringing into the field of influence. And so if I expand this EP to be K, Q, Q over R, and then over Q, what I get is one sec. Yeah, okay. I don't know if I'm doing this right. EP per Q. Which Q am I talking about? Oh, okay, so this is the wrong Q. Sorry. That's the wrong Q. Because the voltage something has, like, if this V here, that I know this is super, super confusing. Okay, this voltage here at A is 100 joules per coulomb, which is created by this big Q. But if I wanted to know how much energy EP little q has at that point, and let's say little q is 1 coulomb, then I would say EP is V times Q. And so it would be 100 joules per coulomb times 1 coulomb, and that would be 100 joules. Okay, so it's how much energy that the charge you bring into the influence of another charge has. I know that's super confusing. Okay, so let me change this to Q. So Q, and we get V equals KQ over R. Okay, so now I can hopefully explain this a little bit better. So we have two formulas, V equals EP over Q and V equals KQ over R. This formula is used to find electric potential. I don't know what to call it. What's it called again? Well, it's called V. Value of V surrounding Q. Okay, so it's found to it's used to find the actual value of the electric potential of V. This is used to find the amount of energy a charge at V has. So at that point in space where you're creating the V with your big Q. I hope that makes sense. It's really confusing. It's all dependent on what Qs you're talking about. So like this one is, and it helps to define which one's which. So this one you're using the Q that creates the V. So it's creating the field. And then this Q is the one that is entering the field that it's already created. Okay, it's kind of like when we had G equals GM over R squared, this was the mass that was creating the gravitational field. And then when we had EP equals, oh, that's not the right one. Yeah, G M1 M2 over R. Then you're bringing, no, that's not the right one. Oh yeah, sorry. Okay, so when we had this, and then we had like FG equals FC. So FG was M times G, right? So GM M over R squared, yep, equals MV squared over R. Okay, this, when you cancel out the mass, you're canceling out the mass of the thing that's in the field, because this is the thing that's creating the gravitational field in the first place. Okay, so it's just finding out which one's which is kind of the hard part. The nice thing about electric potential is that it's scalar and it doesn't matter. There are no vector arrows here at all. And so if in an example like this, where I have 3 point charges, if I were to ask for the electric field at P, you would have to do this. You'd have to do that plus this, okay, and create a triangle. Oh, that's not even a triangle. You'd have to use components for that. But for electric potential at P, you don't have to do that because it's scalar, okay? It's just the value of the thing. So if I want to know like 1, 2, and 3, so V1 will be 9 times 10 to the 9 times, and so this is V created by the charge. Okay, it's the potential at that point. There's no other charge being introduced at P. Okay, I'll explain that in a second. So the electric potential created by charge number 1 is going to be 9 times 10 to the 9 times 3 times 10 to the negative 6 divided by R. So that's 0.05. 1, 2, yeah. And so that's going to be, what is that value? 5.4 times 10 to the 5 volts. And then V2 is going to be 9 times 10 to the 9 times 4 times 10 to the negative 6 equals, oh, this one's a little bit trickier, 514,286 volts. I forgot to divide by 0.07. And then V3 is going to be 9 times 10 to the 9. And if you look on your formula sheet, it says use positives and negatives. So this is going to be negative 2 times 10 to the negative 6 divided by 0.05. And so this is going to be negative 360,000 volts. And so the voltage at P, Vp, is equal to the voltage created by 1 plus the voltage created by 2 plus the voltage created by 3. And so the total voltage at P is going to be all of those added together, which gives you a value of 694,286 volts. Okay? Or if you had, and obviously, like, I'm talking about really, really small charges here. If you placed a charge of 1 coulomb at P, that 1 coulomb would have 694,286 joules of energy. Okay, that one charge. That's what we mean when we do V equals EP per Q. Okay, so if I introduced, because I found the value of V at that point, it's 694,286 volts. And if I had a charge of 1 coulomb at that point, then there would be 694,286 joules of energy at that point. Okay, that charge would have that much energy. Yeah, obviously, charges are much smaller than 1 coulomb, so it wouldn't be that high, but it would actually be like, let's say this is 1 times 10 to the negative 6. Well, then you would have like 1, 2, 3, 4, 5, 6, 0.69 joules of energy. So it's not quite as high. Okay. Any questions about that? I know it can be kind of confusing. Okay. What we know as voltage is actually called potential difference. Okay, and it's defined as, so voltage is actually defined as a change in electric potential. Okay, so it's actually the difference between 2 points in space. So when we talk about voltage of a battery or something like that, you're talking about, so a battery, you have a positive side and a negative side. Well, you have positives on one side, negatives on the other, and there's different potentials there. There's a difference of charge, okay? And so if you take the potential on one side and the potential on the other side and subtract them, you get voltage. And that's what voltage of a battery is. It's the difference between both sides, okay? If we have, so it's beneficial to do it to find the difference between 2 points. So if I have like a positive charge right here, and I have point A and point B, okay, the difference, the potential difference between A and B, so VAB, will actually be VB minus VA. So the difference between A and B, okay, so point A is 0.1 and point B is 0.2. If you were to do V or delta V, it's always 2 minus 1, right? It's final minus initial. So that's why V, the difference between A, B is B minus A, okay? And we already did that. Okay, so if I have something like this, what is the potential difference between points A and B? Okay, I'm going to go VAB, the potential difference between both points is going to be VB minus VA. And so that's going to be 9 times 10 to the 9 times 8 times 10 to the negative 6 divided by 0.5, and then minus 9 times 10 to the 9 times 8 times 10 to the negative 6 divided by 1. And that's going to give me a value of 72,000 volts. Okay, so the difference between both of those points, the difference in potential, the difference between electric potential, it's hard to differentiate between these things, is the voltage. Okay, and so this would, you definitely use volts, okay, when you're doing potential difference. If you're doing electric potential, what's wrong with my pen? Oh no, don't do this again. Okay, electric potential, you can either do volts or you can do, technically the more accurate thing is to do joules per coulomb, but I always do volts because it's the same thing, so it doesn't really matter. So yeah. Okay, I know that was a lot, but we're gonna keep going. Because this is the same stuff. It's not anything new. Okay, we're just talking about work and potential energy. So now changes in energy is the exact same thing. So pretend it's part of lesson 4, and we're just doing more examples. A 4 nanocoulomb, so nano is times 10 to the negative 9, and mass initially at point A, 3 meters from a stationary charge. How much work is required by? Okay, so at point A. Okay, so let's say we have our 6 times 10 to the negative 8 charge right here. Okay, so this is 6 times 10 to the negative 8 coulombs. Our nanocoulomb charge, our 4 times 10 to the negative 9 coulomb charge, is initially at point A. Point A, and this is 3 meters away. 3 meters. Okay. How much work is required by an external agent to move the charge to a point B right here? Okay, where this is 0.5 meters. Now you can ask yourself, what type of energy is this? Is it going to be positive or negative? We are taking a positive charge and moving it closer to a positive charge, which means that it's going to require an input of energy. Okay, and so work will equal delta EP. And so this is going to be EP final minus EP initial. And so it's going to be, we can kind of derive this formula. We don't really have to, but KQ1 Q2 over RF minus KQ1 Q2 over RI. And so if you want to factor some things out, you can just factor the KQs out, KQ1, Q2, and then times 1 over RF minus 1 over RI. Okay, this is sort of like your delta EP for gravity, but because it's not negative in the first place, it's RF minus RI instead of RI and minus RF. Okay, so this is well, let's make it delta EP. Delta EP. Okay, so if we're going to find that, we can go 9 times 10 to the negative 9. 4 times 10 to the negative 9. Why did I do negative 9? 9 times 10 to the 9. 4 times 10 to the negative 9. 6 times 10 to the negative 8. And then 1 over RF, which is 0.5, minus 1 over RI, which is 3. And if we do that, we get a value of, so the work required is 3.6 times 10 to the negative 6 joules. Yeah. Okay. Perfect. And this is positive because we're allowing it to, we're moving it closer. The next part, if we release the 4.0 nanocoulomb charge from point B, what will its velocity be as it passes through point A? Okay, so originally it was at point A. We input energy into it to, like, we're moving it closer, so we're physically doing that. Okay, we move it closer, but now all you have to do is release it, and it's going to be repelled by the 6 times 10 to the negative 8 charge. And so what happens is you have this 6 times 10 to the negative 8 charge, coulomb charge, and then we have our 4 times 10 to the negative 9 charge at 0.5 meters away. And if we release it, it's going to be flying this way. It's going to be going that way at some v when it passes back through point A, okay? And point A is 3 meters away. So what we can do is we can say, okay, what is its energy at B? Compare that to the energy at A. So it's going to have EPI at B. Its EK at B is going to be 0. Okay, because it's just moving, we're holding it there. And then when you release it, it's going to move past point A. So EPF is we don't know. And then EK is what we're trying to find, because that's what we're going to use to find the velocity. Okay, and it still has potential energy at A because it's still 3 meters away. It's still in that area of influence. Okay, so we're going to go back to this formula we had before. Delta EP equals negative delta EK. Still applies. Okay, and remember that this is from conservation of energy. That's where this formula is coming from. And so this is pretty much all we need to do. Now, this delta EP is going to be KQ1 Q2 1 over RF minus 1 over RI equals EKI is nothing, so negative EKF. Okay. So 9 times 10 to the 9, 4 times 10 to the negative 9, 6 times 10 to the negative 8, 1 over 3 minus 1 over 0.5 equals, and then this is going to be negative 1/2 times m. M was 2.4 times 10 to the negative 21, and then v squared. Okay, now notice how the delta EP is just switched. It's instead of going from 3 to 0.5, it's going from 0.5 to 3. And so it stands to reason that this side of the equation should be negative 3.6 times 10 to the negative 6 joules. Okay, I'm not going to write joules. Because it's the exact opposite work. Okay, instead of inputting that work, you're releasing that amount of energy. Okay, so that's where that should make sense. Now this is negative 1/2, still 2.4 times 10 to the negative 11 times v squared. And if you need like mass of an electron, mass of proton, charge of proton, charge of an electron, charge of alpha particle, mass of alpha particle, those things are on the constant page of your formula sheet. So just look for those. And like obviously the charge of a proton is the exact same thing as the charge of an electron. So they're together there. Okay, continuing on this question, negatives cancel out. Multiply that side by 2, divide by 2.4 times negative 21, and you get V equals 5.5 times 10 to the 7 meters per second. Boom, like that. Okay. Now, if hopefully that makes sense. If you're solving questions that have V, and your answer comes out to be something like 6.2 times 10 to the 12 meters per second, there's an issue there, okay? And that issue is this is the max speed you can ever get. Okay, you cannot get faster than that. This is the speed of light. Okay, and so if you get 6.2 times 10 to the 12 meters per second, you did something wrong. Or you're not factoring in the fact that like it probably won't, but it might reach that fast, like if your math comes out that way. But it's pretty impossible. So yeah, even if I made this infinity, like if I said, okay, what's its speed at infinity? Well, then it would be, yeah, so let's do that. So let's say we have this charge, and then we're saying what's its speed at infinity? So R equals infinity, okay? So if we do this, we have EPI and we have EKF. Okay, EPF is 0 because it's at infinity, EKI is 0. So we have EPI equals, I'm trying to do this in my head, delta EP negative EKF. Is that right? Okay, give me a sec. Oh yeah, no, this is negative, right? Because EPF is 0, so it subtracts. Okay, there we go. Now they can cancel out. Just trying to figure that out. Okay, so it's 9 times 10 to the 9 times, where are my numbers? Where'd they go? Oh, there. 6 times 10 to the negative 8. Come on. 4 times 10 to the negative 9 over 0.5 equals, and then this is 1/2 mv squared. And so if I were to do that, that would come out to be 9 times 10 to the 9 times 6 times 10 to the negative 8 times 4 times 10 to the negative 9 divided by 0.5, and then times by 2, divide by, what's our mass? 2.4 times 10 to the negative 21, and then square root that. My answer comes out to be 6 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters per second. Okay, and keep in mind that it's accelerating this whole time. Okay, so that's faster than it was before, than right here, but it's still not over our speed of light. So it shouldn't be faster than the speed of light. Okay, your answers, none of your answers should be. Okay. Last thing is called equipotential lines. Okay. I know it sounds kind of confusing. So the idea here is that if you have a charge, the point, let's say we have a point right here on this side, okay? How will that compare to a point on the other side that is the exact same distance away? Okay, and the answer is it's the exact same potential energy. It's the exact same electric potential. Everything about that point is the exact same. It's just going in a different direction. But because we're talking about energy, it doesn't matter. Okay, and so what we do is we kind of draw these orbits around the charge, and we say the amount of work to travel along an equipotential line, I'm just going to write line, is 0. Okay, so if I wanted to move from here to here, that would require 0 work because I'm not changing energy. It's the exact same amount of energy. Okay, the work comes into play when I want to change orbits. Okay, changing orbits requires energy. Okay. And this shouldn't come as a huge surprise. And in fact, I'm hoping some of you are applying your chemistry minds and thinking, hey, that kind of looks familiar. Okay. If you know anything about chemistry and atoms, what's in the middle of an atom is a positive nucleus, and what's surrounding is orbits of electrons. Okay. And why are they in orbits? Because they have certain amounts of energy applied to them. Okay, if the reason Niels Bohr found out about these shells of electrons or these electron orbits is because he saw energy being released when an electron would flip, when would change orbits. Okay, and so that's the whole point of this, that there's a change in energy when an electron changes orbit surrounding a nucleus. Okay, so it's kind of an application here of where physics meets chemistry. So that's kind of cool. What else do I want to say about this? I think that's it for that. We won't talk about that today. We'll do that on Tuesday. Yeah, I think that's it for today. Any questions? That was probably a lot. That was pretty good. Anyone? You guys just want to start the weekend, hey? So in terms of the assignment, it's kind of like meant as an ongoing thing. So you had the ability to do the first two quizzes, I guess you want to call them, yesterday, and I haven't looked at it lately, so I don't know if you can do the next one yet, but you could probably do the next one. And then after Tuesday, you can do the next one. And the idea is that on Tuesday, we're going to finish the last two lessons, and then all you have to do is finish the one quiz and then hand it in all together. So that one will be due like Tuesday, like noonish, okay, or afternoon sometime. That way I can get it marked and back to you on Wednesday. And then Wednesday, you're just going to ask me a bunch of questions, kind of like a review day. And then once we're done that, I'll post the test. Okay, and then you'll have till probably Thursday morning sometime. But like my marks have to be on Thursday afternoon, so it's like there's going to be a cutoff there. You can't just hand it in super late. So that's the plan. And remember that there's no school on Monday, so don't show up here on Monday because I won't be here. Okay, any last minute questions? I don't get that one. 9.8 times 10 to the 6 is positive. Where? 9.8 times 10 to the 6. Where is that? I don't see that number anywhere. The last solving question. What number? 9.8 times 10 to the 6. I don't see that number anywhere. Where is that? 9.8 times 10 to the 6. Nine times 10 to the 9. That's the constant. That's Coulomb's constant. That's K. Kanwu, you and I can chat if you still have questions at the end, okay? Okay, so that's it for everyone else. Have a great weekend, and I will see you on Tuesday.